So we're going to do an exponential decay application problem. In this problem, we're going to consider the number of farms represented by the variable n. The number of farms in the U.S. has declined continuously since 1950. And we know that in 1950, there were 5.6 million farms. And in 2008, that number had declined or decreased to 2.2 million. If we assume an exponential decay model, let us find the decay rate. So we have information, we have data regarding when we began keeping this data in 1950, how many farms there were. And then in 2008, which is 58 years later, we know that there were less farms, 2.2 million. So since this says exponential decay model, exponential, that word lets me know I can use my PERT formula. A equals PE to the RT. So we need to determine what the rate is. We are asked to find the rate. So that means I need to know, if I want to find what rate is, I need to fill in a value for A, my end amount, P, my starting amount, and T, how much time has elapsed. So we know how much we started with. We started with 5.6 million farms, and we ended with 2.2 million. So 2.2 equals 5.6 E. And how much time has elapsed between 1950 and 2008? And if I do a quick subtraction, I will get 58 years. So that means R times 58 is in my exponent. And I paused it and rewrote it just to make it look a little neater. So if we want to solve for R, it's in the exponent, we're going to need to use logarithms. Our first step will be to divide on both sides by that value 5.6. So I get 2.2 over 5.6 equals E to the 58R. And I can use my calculator or some simple algebra to rewrite that fraction as 11 over 28. You could multiply by 10 over 10 and then reduce that by dividing both of those terms by 2. So we end up here with 11 over 28 equals E to the 58R. So in order to solve for this, we're going to take the natural log. So the natural log of 11 over 28, the natural log of E cancels, and I end up with just 58R. And we know a property, we learned it, log base B of B to the X equals X. So since we know that property, if I take the natural log of E to the 58R, since natural log is base E and exponential in the argument is base E, we can simplify this to 58R. So now all I have left is to divide by that 58. So the natural log of 11 over 28 divided by 58 will equal my decay rate, R. Typing that into my calculator, I get negative 0.01610878. So this represents my decay rate. Now, I want to make sure we notice we're talking about significant digits or significant figures. So that means we keep however many digits once the zeros stop. I'm going to keep 3 digits. So 3 digits in this situation when I'm rounding means I'm going to keep that 1, 6, and 1. And everything else we're going to consider insignificant and we're not going to use. So my decay rate can be written as R equals negative 0.0161. Now that we know the rate, we can use this decay rate to let us write a function, an exponential function that's going to model the situation. So, again, using my PERT formula, my end amount at time t, a of t, and I know I left that off up here, but it's just a matter of abbreviating, and I wasn't using a formal notation, so it was okay to leave that a of t off. But when I write my function, I really want this a of t. I'm saying this is a function, my end amount at time t. So a of t equals my initial amount, 5.6 e, to the rt. Now, t is an independent variable. The amount of time can change. So I'm only going to put my r in, 0.0161, and I'm going to leave my t value. So remember, if we have a function, we have to have an independent variable or an input, in this case t, and an dependent variable or output, a of t. All right, so in order for this to be a function, it must have this input and output value. So now we have a function. We can use that to predict or model for future situations. So our next step might be to estimate the number of farms in 2016. So remember, our initial data, we started in 1950 keeping data. So we want to know the number of farms, which is my end amount, a of t, in 2016. So that means I know a time value. And what does time equal in this situation? So because we're dealing with 2016, that is 66 years after 1950. So a of 66 equals 5.6 e to the negative 0.0161 times 66. So at this point, we can plug this right into our calculator. And we get this output value, 1.935, with continuing decimals. So does that mean in 2016 there were 1.9 farms? That doesn't make any sense. Let's go back up and reread our problem. So you want to notice that when we talk about our numbers of farms, they are in millions. And I didn't use that million value in my problem. So, in order to find out or interpret this answer as how many farms, we need to take this number and multiply it times 1 million. And if I do that, that's going to cause that decimal to move 6 places to the right. So, this gives me a value of 1,935,114.693. So that is how many farms we have. But, I wanted to keep this interesting for us. So you'll notice I have in here round to the nearest 1,000. And that says thousand, not thousandth. Tenths, hundredths, thousandths is behind. If I put a TH there, we would be rounding to that 3 value. But we don't have a TH there. So in this situation, we're going to round to the thousands place. And the thousands place is this 5. So my final answer would be 1,935,000 farms. So rounding appropriately, this is what I would get right here. Okay, Lastly, the last part of this problem, we need to predict when the number of farms will decline to 900,000. So again, remember, we are measuring farms in millions. So if we're talking about farms, I need to convert this number to millions. 900,000 as millions, I would divide by 1 million, and that would be when our end amount, A of t, is 0.9 million. 9/10 of a million is 900,000. So this is solving the exponential equation using that same formula. 0.9 equals 5.6 e to the negative 0.1 or 0.161 t. So t is my variable here because we are looking for when, right? That's what we're solving for. So we know the end amount, we want to find that time. So we'll solve this problem. I'll divide on both sides by 5.6. 0.9 over 5.6 equals e to the negative 0.0161 t. 0.9 over 5.6 simplifies to the fraction 9/56. So I have 9 over 56 equals e to the negative 0.0161 t. And of course, solving this like we did in our previous two word problem examples, I'm going to take the natural log of both sides, the natural log of 9 over 56, and when I take the natural log of e, that's going to cancel, and I just get the exponential argument, negative 0.0161 t. And at this point, I will divide. So dividing by negative 0.0161, that will give me my t value. And this gives me an output of t is approximately 113.5482679. So rounding to the nearest whole number, well, that would round to either 113 or 114. This represents my t amount. So that is 114 years. So 114 years later, 114 years after our initial year, and the initial year was 1950. So if I add that to 1950, I get in the year 2064. So that is when we can predict, using this exponential decay model, that the number of farms will decline to 900,000 farms. And so you see here we have developed a exponential model. We've found the decay rate to plug into that exponential model. We've used the model to solve for a amount at time t, and then also to solve for the time that an amount will become a specific value, in this case 900,000.